All right, we're back recording, going here, and start. When you look at the speedometer in a moving car, you see that cars. Yeah, instantaneous speed. How fast are you going at that instant? Instantaneous speed. Points on the board. Ooh. Stevens in the lead. Train travels 7 meters in the first second, 7 meters in the next second, 7 meters in the next second. What is the acceleration of that train? Yeah, 0 meters per second squared because it's not changing what it's doing, right? So you could say its velocity is 7 meters per second, but its acceleration then would be 0 meters per second squared. It's not speeding up or slowing down. For that matter, going around a curve. Right? Car starts from rest and after 7 seconds picks up to 42 meters per second. What was the car's acceleration? Yeah, 6 meters per second squared. That's a second kinematic equation. Velocity final equals initial velocity plus acceleration times time. 7 times 6 is 42. There you go. And the units. All right. Got Catherine, Sohan, Stephen, Max, Stephen. Object falls freely in a vacuum. It's I'm looking for velocity increases, but the acceleration stays constant. Here, let me flip my screen over here and show you guys the poster version of this. You guys remember drop a ball off the edge of a cliff? So it looks like I take a picture every second. Ooh, look at that. The ball's like spreading out, right? So what's going on second by second? Oh, the acceleration is the same all the way down, 10 meters per second squared, which means that the velocity changes at a constant rate. Right? It's picking up 10 meters per second every second. Right? And then, okay, so the distance, is a little bit more complicated. It looks like it's like spreading out, right? That's a parabolic relationship with time, right? Like 1/2 GT squared. All right, so we got all that. Back over here. Oh, Catherine to the top. Melissa. Hey, Stephen, Max. Okay. Oh, sorry. The absence of air resistance. Objects fall at constant. Acceleration, yeah, constant acceleration. Right? Same as the poster I just showed you, right? And for Earth, that would be about 10 meters per second squared. I got Stephen, Sarah, Stephen, Melissa, Catherine, fire. Suppose an object is in free fall. Each second the object falls. Yeah, a larger distance than the previous second, right? Remember the like if you take a picture every second, it's like spreading out. So it's speeding up, right? Speeding up at a uniform rate. All right. Ball tossed vertically upward, rises, reaches highest point, falls back down. During this time, acceleration is directed downward, right? So you throw no while you're throwing it. Of course, it's accelerating up briefly, but as soon as it leaves your hand, it's in free fall. It's accelerating downward. While it's moving up, it's accelerating down. At the top, it's accelerating down. When it's moving down, it's accelerating down. Gravity is always pulling down while it's in free fall. I got Max, Addie, Steven, Catherine. Ball's thrown straight up. At the top of its path, its instantaneous speed is Yeah, 0 meters per second. Right? If you guys ever see a question in a physics book that says something about maximum height, you might have to remember that in the back of your mind. Oh yeah, okay, that means the velocity at that point is 0 meters per second, and then maybe you could solve for something like how fast did I throw it? All right, here we go. Ball is thrown straight up at the top of its path. Its acceleration is about 10 meters per second squared, right? And of course, directed downward, right? Always in free fall. It's accelerating down at that rate. Always in free fall. Car accelerates at 2 meters per second squared. It starts from rest. How much time to pick up to 20 meters per second? Yeah, 10 seconds. So it's also the second kinematic formula. Right? The velocity picks up to is initial velocity plus acceleration times time. 2 times 10 is 20. There you go. And the units. Right. Ooh. Got Steven, Catherine, Melissa, Max, Steven. Ooh. I'm sorry, Steven. If for the following object equipped with speedometer, its speed reading would increase each second by 10 meters per second. Yeah, there you go. Picks up 10 meters per second per passing second. All right. For the following object starts from rest after falling for 2 seconds, pick up to a speed of about 20 meters per second. GT. 10 times 2 is 20. And then the units, meters per second. Right. Melissa, Addie, Catherine, Max, Steven. Ball is thrown to the air at some angle. At the very top of the ball's path, its velocity is yeah, entirely horizontal. Okay, you guys got that? Awesome. No, this one I was gonna draw anyway, especially for the recording. Number of students have been just this day, so I wanted to get you guys a picture. So here we got the ground down here. We're throwing the ball at about ground level at some velocity. So that'd be throw, right? So that's some speed at some angle. So like relative to the ground, for example, call it theta. Okay. So then it's gonna do well. It's gonna go into parabola path and land. Bam. Okay. So the way we've done analysis for projectiles, tell you guys, well, first thing you want to do is like break this into components. Say, how fast is it going across and how fast is it going strictly up? I'll call this v sub x and the initial in the y direction. Right? If you like, you can throw little vector arrows above those. Right? Then what about the very top of its path? Right? Well, the very top of its path, it'd be going actually like this right here. Right? I'll call it v sub x. Right? And I'll notice the horizontal component of velocity stays the same throughout the flight. Right? And at the very top, it's moving entirely horizontally. Okay. Now the vertical is first a little more complicated because gravity is pulling vertically. So it's slowing down on the way up and then speeding up on the way down vertically. Right? But horizontally, so all the way across. Right. All right. Steven, on fire. Ball thrown into the air will never go as far as physics ideally would predict. Why? Why does it always land a little bit short of? Oh, there you go. All right. Yeah, air friction slows the ball. That's another one. Yeah, you guys really good compared to some of my earlier classes, right? So here's the premise. Let's say we sit here in class and say, well, if I throw this ball at this speed at this angle, it should land like 50 meters away. Then we go into the field behind the skull and it only lands like 40 meters away. Or maybe it's a wiffle ball and only lands like 10 meters away. It's like, why is it always landing like short? Because in our equations, we're going to neglect air drag, right? We're considering how fast we're throwing. We're considering gravity in the equations, but we're ignoring air drag, right? So it's very simple parabola shape. When you clear air drag, it gets really complicated. All right, Max, on fire, too tough. True or false? In the absence of air friction, the horizontal component of a projectile velocity does not change. True. Oh, everybody got it. Everybody got it. Yeah, exactly, because that's the same as my picture that I just drew for you guys. All right. All right. I know it's like weird negative phrasing too, and a true or false. So you guys got the wording too. All right. At the same time, a ball is thrown horizontally, and another ball is dropped from the same height. Which ball hits the ground first? Yeah, same time. Right. They have the same vertical motion. If you throw a ball horizontal and drop a ball, yeah, same vertical motion, hit the ground same time. Yeah. I could totally see AP asking that question as a conceptual, maybe a multiple choice question. Be a good question. Airplane flying 40 meter per second north enters a 30 meter per second eastward crosswind. What is the plane's ground speed? How fast is it moving compared to the ground? Uh, yeah, there you go, 50 meters per second. So that's like if you're standing on the ground, you point a radar gun up at the plane. Or if you consider like the plane shadow moving across the ground. Here, let me draw this one up. So we got a plane, right. Say we're looking down from above. Maybe we're in a higher plane. And then this plane's moving at 40 meters per second straight north. Right? There's like this eastward crosswind. Now I'm going to connect these vectors tip to tail. You guys remember vector addition? Geometric vector addition. You can do this tip to tail. The plane's always flying north. The wind's always blowing east. Right? So tip to tail vector connection. Meters per second. Right? Now, here's plane relative to the surrounding air. Here's air relative to the surrounding ground. Add those two together, I'll go from the tail of the first vector to the tip of the last vector. This is called the resultant vector. And that tells you the speed and direction of the plane. Right? Pythagorean theorem, you guys see a 3, 4, 5 before setup, right? So if you square root of 30 squared plus 40 squared, 50 meters per second. Right. Hey, how about this? Do you guys remember? No, that's the plane shadow moving across the ground, right? Is going 50 meters per second. Even though the plane's pointed north, it's being blown off course of it northeast. Okay. Who remembers? How do you get that angle right there? Inverse tan 30 on 40, and the units cancel. And who remembers what that angle is for the special looking triangle? About 37 degrees, right? And what is this angle up here? About 53 degrees up here. Right, guys, if you ever see a 37-degree angle or a 53-degree angle being set up, there's a good chance that it was specifically picked for 3, 4, 5 type geometry, right? So they, okay, well, this vector is going to break into components, but they're setting up some kind of proportionality like that. That's what you should be looking for. There's like a ball kicked at a 53-degree angle. Okay, all right. Oh, what's the resultant of 3-unit vector and 4-unit vector at right angles? Bam. There's the answer right there, right? There you go. The answer was right there. And very similar to what we just did. Pythagorean theorem. So 3, 4, 5, special right triangle. Got Catherine, Stephen, Addie, Max on fire. When in orbit, a satellite such as a space shuttle is. No. All right, so this one's a little tricky, right? Usually projectiles, I tell you, oh, so it's a parabola shape, but that's not actually true for this one. So this is actually a special projectile, right? If you throw something to the right fast enough, then it can actually like orbit the Earth. Now it'd be crazy fast, right? It's about 8,000 meters per second, right? So it's a circular orbit, right? But it's definitely not the other two if you did process of elimination, because the fact that it's on a curved path means that it can never be the blue one, right? Not non-accelerated means it's okay, not speeding up or slowing down, but also not on a curved path, right? So its weight is acting as the centripetal force. Okay, so can't be the blue one. Right? Oh, also not the yellow one. Even though if you were inside the space shuttle orbiting, you might feel like you were free from Earth's gravity, but that's not actually true either, right? So you're just in free fall. You're just falling around the curvature of the Earth. Yeah, so it's a special kind of projectile. That was a little tricky. The law of inertia. Yeah. At rest will remain at rest until outside force. Continue moving in a straight line until there's outside force. Continue moving at the same velocity until there's outside force. All the above. Yeah, all the above. Those are all true statements, right? So law of inertia. That's the Newton's first law of motion. Right? Nothing, guys. If you ever see anything speeding up, slowing down, or moving on a curved path, then there must be an external force acting on that object. Right? External net force. All right, Addy, moving to the top. After a cannonball is fired into frictionless space, the amount of force needed to keep it going. Voyager spacecraft. 0 newtons. Right? Like that Voyager spacecraft I was using as an example. Right? That was launched way back in the 1970s. It's still going today. Right? Still moving away from Earth. Right? Now, it hasn't been burning rocket fuel for like the last 50 years. No, it doesn't. It's just inertia. It's just going. Just inertia. It's just going. Max to the top. If the force of gravity suddenly stopped acting on the planets, they would. The color's matched. Which color is it? The color. Straight line tangent to their orbit. Right. Let me draw that out real fast. I'm gonna switch back over here. Let's draw that real fast. Right. So I got sun. Right, here's the orbit of a planet. Ooh, elliptical orbit. Right. Now, at any particular instant, it has a velocity that's tangent to its orbit. Right. So tangent to its orbit is like if I hold my ruler flush to the curve, flush, like right there. At this exact moment, it's going kind of this way. I call it velocity vector, right? Right. So if gravity suddenly boom, turned off, it was right, Newton's first law of motion. Just keep flying in a straight line. Just a like of that. All right, Max holding on to the lead. Sheet of paper withdrawn from under a container of milk without toppling the paper if it's jerked quickly because. Oh. Yeah, inertia. And my earlier classes wanted to see the old Paul Hewitt, so let's bring the Paul Hewitt on this one. How about that? Physics is fun. Oh yeah. Inertia. Right, wants to sit right there. Inertia. Max on fire. Get the lead. Force required to maintain an object at constant speed in free space is equal to. Hey, this sounds like Voyager space. 0 newtons. Oh yeah, 0 newtons. Just inertia. Just going. Right, Melissa, Steven, Addie, Max. Acceleration is a change in change in velocity per change in unit time, right? Yeah, I'm gonna bring another Paul Hewitt example for this one. If you pick the green one, some of you guys did. His example is like, let's say you buy an old used car, and the car dealer salesman was like, "Hey, this car don't look too good, but oh, man, this car will go 0 to 60, 0 to 60, right?" That's like if you pick the green one. You say, "Wait a minute," and then you drive. It's like it takes like a whole hour to get up to say, okay, this car accelerates so slow. But if it's like 0 to 60 in like so many seconds, like in 8 seconds, like okay, now it's telling you something about acceleration, right? It's a rate change of velocity. Rate change of velocity. Change of velocity per change in time. Here, let me flash the poster up here real fast. Talking about, we're talking about this linear acceleration, right? Change of velocity per change in time. There you go. Right. Ooh, meters per second per passing second. It's called meters per second squared. Right on. Acceleration produced by a net force on an object is. All right. Yeah, so those are all true statements. Directly proportional to the net force, inversely proportional to the mass, in the same direction as the net force. Right. Those are all parts of this right here, Newton's second law of motion. Okay. See, back in kinematic days, we were okay. Like here's the kinematic days, right? So okay, acceleration is a rate change of velocity, right? This should right. Here's rate change of velocity, right? Now we're saying, how do you get acceleration? Well, you get acceleration by force acting on a mass, a net force, right? So there's like 10 different forces. You got to find the net force. More force, more acceleration. More mass, less acceleration. And then the acceleration is the same direction as the net force. Boom. There's all of them, all the above. All right. Oh, Steven, top spot. Equilibrium. Yep, these are all true. So the net force is 0. If you introduce a Cartesian system, the components also zero out along each axis. Torque zeroes out. Those are all parts of equilibrium. All right, Max, back to the top. Girl weighs 500 newtons, hangs from the middle of a bar supported by 2 vertical ropes. What's the tension in each rope? It's 2 ropes. There you go. So 250 split. Now that's if she's hanging in the middle. If she's hanging anywhere else, well, you got to bring in torque and say, okay. But you guys do know the 2 ropes always add up to her weight, right? So regardless of where she's holding, right? All right. Friction is a force that always acts. Yeah, opposite of object's motion, right? So we're getting close to talking about free body diagrams. Do you guys remember free body diagrams? They say only label the forces, and maybe more recently the torques also, right? But don't really label velocities, right? Especially for AP, they'll mark you wrong, right? But sometimes it's good to know the context of velocity for this exact reason, right? If something's sliding a certain direction, you want to know that so you can correctly label friction as opposing that direction, right? All right, Addy moving up, Max still in the lead. What is the maximum resultant possible from 2 newtons and 8 newtons? Yeah, 10 newtons. There you go. All right, so you and a friend are pushing 2 newtons, 8 newtons, same direction. Tip to tail, vector addition. Yeah, 8 plus 2 is 10. All right. Stay moving up. Max in the lead. What is the tension? And each of the 3 ropes at 120 degrees from each other. So these 3 ropes up here, all going together. Oh, I got a 100 Newton lantern. Might need to add some time to that one. Or here. Yeah, I think I need to throw a few more seconds on that one. But let me go and draw this one out anyway. Okay. So just an old classic question right here. Right. So I got these 3 ropes, right? All we got some radial symmetry, right? 120 degrees, 120 degrees, 120 degrees, right? Now, from the point of view of the central point, got 100 Newton lantern acting straight down. I could do from the point of view of the lantern, 100 newtons down, 100 newtons tension up. Okay, so this is 100 newtons. I got switch color here for angles. 120 degrees, 120 degrees, 120 degrees, right? Force, right? What if I change the story? Guys, would this be mathematically equivalent to, what if there was three guys in a big field playing three-way tug-of-war, and we're up in a helicopter looking straight down, right? Guys, the fact that there's radial symmetry, you guys see if this guy's pulling with 100 newtons. Well, this must also be 100 newtons on 100 newtons, right? From a radial symmetry point of view, right? Now, our usual method, like more, I guess I could, what if you change the angle? You could still solve it, right? Is to break these into components. So I'll say, well, say like you were solving for this, I have a Cartesian system. Maybe I'll say this guy's pulling a little bit to the left, this guy's pulling a little bit to the right, this guy's pulling up a bit, this guy's pulling up a bit. Oh, so now I have component vectors, left, up, right. You say the left and the right are balanced, right? And then this up and this up sum to like this down, so it sums to 0, right? Up and up, and then down sums to 0, right? Guys, what is this angle right here? 30 degrees, right? And then here's 60 degrees up here. Here's 9. Hey, that's a 30, 60, 90 triangle, isn't it? Right? You guys remember for this purport, right? This would be then 50 newtons, which is half of this is 100 newtons for that 30, 60, 90 triangle, right? All right. Got that. All right. Old hanging lantern. Okay. I got Melissa, Addie, Steven, Max. Which has more mass? Kilogram of feathers, kilogram of iron. Same mass, 1 kilogram, same inertia, different volumes, different densities, yeah, same mass. Sarah hopping back in top 5, Max still in the lead. Accelerations are produced by, what causes acceleration? Forces. That there's Newton's second law of motion, right? Forces acting on masses. Right? The more force, the more acceleration. Right? Right. Why does anything accelerate? Well, because there's a force acting on it. Ooh. Max got a slim lead still. How does acceleration change in relation to mass? Right. The more mass, the very helpful question. Okay, there's an inverse relationship between mass and acceleration. Here, let me bring this over here and let's get a flip over here. Okay. Let's get a good look at this one. Okay. So the question was, what's the relationship between mass and acceleration? Right. Now, of course, this is the same equation, but a little bit different perspectives, right? Okay. So the more mass, the less acceleration. You guys remember if there's like this guy versus this guy, and you put a force, equal force on them? Right. Look at this guy. Look at this guy. Right. So while you're applying the force, right? Large mass has a small acceleration. Right. You guys definitely see an inverse relationship right here between these two, right? Now, it's the same relationship here, because whenever there's two variables multiplied on the same side, they have an inverse relationship. So for the same force, right, a large mass results in a smaller acceleration. Make it that way. Back to Kahoot. And you guys good with that? All right. If you made a graph of mass versus acceleration, be like inverse relationship. All right. Max on fire. When an object reaches terminal velocity, its acceleration is. Yeah, 0 meters per second squared. Now, to have terminal velocity, you need something that we normally ignore in this class, which is air drag, right? If there was no, guys, if there was no air drag, if in a vacuum, can you ever reach terminal velocity in a vacuum? No, right? You need air drag to make this happen, right? So the faster it falls, the more the air drag picks up until it reaches the state here. All right, then it just falls with some velocity, just a constant velocity. So there's no more acceleration. 0 net force, 0 acceleration. That is an example of equilibrium. Book weighs 4 newtons. When held at rest in your hands, the net force is. What's the net force of anything at rest? 0. If you draw a free body diagram on books, say, okay, got 4 newtons downward, the weight, and collectively 4 newtons upward, the force from your hands, it zeroes out. So the net force is 0, acceleration is 0. Anything at rest has 0 net force because that's a type of equilibrium, right? Maybe the most obvious type of equilibrium. Right? If you pull a 10-kilogram wagon with the 20 Newton force, let's say you're pulling horizontally, right? What's the acceleration? 20 newtons on 10 kilograms. There you go, Newton's second law of motion. 20 newtons on 10 kilograms, 2 meters per second squared. Right? Now that's really if it's the net force. I could see AP asking a more complicated version of this. Guys, what if she pulls straight up? Wouldn't you also have to subtract the weight of the wagon before you divide, right? Okay. So if you're pulling straight up, you say, well, the pulling force minus the weight, and then divide by the mass, which is a little bit more complicated, right? But this comes out of a conceptual book right here. Right? All right. A constant force produces a constant. Acceleration, right? That's Newton's second law, right? A constant net force, constant acceleration. F equals ma, right? There's a constant force, you're either speeding up or slowing down, or going around a curve, I guess, right? All right. Ooh, Mac's still holding on to that slim lead. Look at there, the whole time. Suppose friction force of a sliding object is 35 newtons. What's the force required to maintain a constant velocity? Yeah, also 35 newtons. Okay, now that is here, that's this right here, right? Right. One of your labs had you figure out coefficient of friction using this particular method, right? So, guys, constant velocity, that's equilibrium, right? Constant velocity is equilibrium, which means all the forces balance. These two forces balance, these two forces balance. So if your spring scale is rating 35 newtons, that tells you friction force must also be 35 newtons, as long as it's constant velocity, right? Start B. And for the win. Aunt Benny throws one rock and drops another. The acceleration of the rock after it's thrown is how compared to the dropped rock after it leaves her hand. Yeah, the same. Okay. Now remember, this is after it leaves her hand. After it leaves her hand, it's in free fall. Right? Right. Now it might be moving a different speed, different direction. That doesn't matter. Right. Once it leaves your hand, it's in free fall, accelerating down at about 10 meters per second squared. All right, to the podium with the bronze, Eddie. With the silver, Steven. And the gold, Max. Runners up, Sarah. All right, nice job. Nice job. All right, so this.